Friday, May the 19th. I've just finished making the Maple program that I stated I would to solve two of the last three problems. It took practically all day. I just had time to take a trip to town and buy coffee. Otherwise, I've been reading the paper too and doing a little stuff, but I've spent, I guess, 5 hours at the screen fighting with Maple. One of the problems was that factorizing gives a strange data structure that I find it difficult to apply. You see, when we factor something in Maple, then we get this structure. So this is a product of two factors, and this is not an integer, it's a special data structure. And I don't know what it really is, but you can't say 6 divided by this, it won't compute. One can make it compute like by using the expand command on this and on this. If you say expand of this, then you do get 4. So what I needed was to get the operators. So the first was to, another thing I decided along the way was to only make B one point m, because then it's easy to get them all just by multiplying them with a Kronecker symbol. Here I take the matrix I wrote many problems ago, and it needs to be, the way we access it here, it needs to be transposed. But we have a prime number, then we factor it and take the first factor, and then we must multiply it by this unit of so that it becomes equivalent to 1 modulo 4, and that's given by this. The next step was to find the B of the product of the powers, and that's exactly what we did in one of the problems. That was problem 3 of this section. So if P is even, then it vanishes. If E is -1, then it's set to 0. And if E is 0, then the prime power is unity. So B must be unity. And if it's the prime itself, then it's 2 times A1 of P. And if E is larger than 1, then we use the recursion formula, where I just write up. And then for each of these, there are some test cases. And I really had to work a lot on this to make the test cases work. But that's just usual. The worst problem was that I didn't access this data structure correctly. This is B1 of the prime powers, yes. And then we can actually take the values of the B values when n is equal to unity. and that's just using the same formula. It's a prime factor, then we use the prime factor, and if not, we just write it into a product of two mutually prime numbers and take those and multiply, then things are okay. And this is in case it's a prime. That's really weird. I thought that was solved up here. Well, never mind. That's something I would look into if I had to work more on it to make it more pretty. And then we check B1 with the expansion I've made. This is in the book, and this is what I computed solving one of the previous problems. And now this assumes that m is odd. Yes. So we have to multiply B1m with this, with the Kronecker symbol. Oh, so that's actually B itself we have here. Yes. So now we can compute the value of the L function at s equals unity. So we enter to the product n, defining the elliptic curve, and the number of digits we want in the result. First, what's called square root n mark in the text. Then theta, as I've already defined in the earlier exercises. Then we find out how far we must, how far up we must sum. And I put the limit to be 1/2, so the residue is less than 1/2 to 10 to minus digits. And oops, this is wrong. We have to do the, oh yeah, never mind. So we can't do that. We just delete that. So that's why the results were a little imprecise. So we'll just do it again. You know what, I'll just compute everything here. There we go. So the last computation takes sort of 10 seconds, I guess. Oh, my God, I really did change something here, which I shouldn't have changed. You can see this is really nonsense. That really didn't take a long time, and I have no idea what went wrong. But now it works. All I had to do was really to press this button once again, and then it worked. What this button does is to compute the whole script. So first we compute the value for n equals unity 2 and 3 with 4 digits, as we have already done before. And then we verify the result with 38 digits so that we can compare them with the result from Paris. They agree. It's lovely. And then one of the problems was to prove that this was non-zero. And then 41, we found out in chapter 1, section 1, in the first section, that this is a congruent number, so it should vanish, and indeed it does seem to vanish. And you can see we get very precise results now, as expected. Well, that was... This should actually have been the end of the section, to be able to make this procedure and make these calculations. But I did it before the next to last problem, so I still need to do one problem before I can say chapter 2 done.